Next up, we have hybridization and the formation of hybrid orbitals, they're called. Recall that the word hybrid refers to a combination of different things to make something new, like a hybrid vehicle, something that runs on both gasoline and electricity. There's lots of examples of hybrid fruits, such as a tangelo, which is a hybrid between a tangerine and an orange. Pluots, that's a hybrid mix between a plum and an apricot, and there's all kinds of examples of these. So hybrid orbitals says when the central atoms in a molecule or polyatomic ion form, when the central atoms in a molecule or polyatomic ion form bonds, they usually form, not always, but we'll assume that they do, they usually form these things called hybrid orbitals. So hybrid orbitals are a mixture of atomic orbitals. So by atomic orbitals, I mean s orbitals and p orbitals, and sometimes even d orbitals can combine to make these new hybrid orbitals. So here's how it works. In a molecular polyatomic ion, the electron groups around the central atom, now that can be bonding pairs of electrons or lone pairs, will be found in hybrid orbitals. So we want to look at the central atom, see how many electron groups are around the central atom. That will then be the same as the number of hybrid orbitals, which will be the same as the number of atomic orbitals that combine to give rise to those hybrid orbitals. Let me show you what I mean. The first example here is formation of sp hybrid orbitals. And so it says that the electrons are localized in two regions around the central atom. So the example we're going to look at is BeCl2. So let's look at the structure. I'm not going to put the lone pairs of electrons on the bonded atoms because I just want to look and focus on the central atom. So beryllium, the central atom, has two electron groups. In order to accommodate those two electron groups, it needs to form two hybrid orbitals. In order to form two hybrid orbitals, two atomic orbitals need to combine. Now, these atomic orbitals that combine are in the valence shell. So let's take a look at the orbital diagram for beryllium, just the valence shell. Now remember that in order for covalent bonds to form, we need half-filled orbitals to overlap. And so just beryllium itself, the neutral atom beryllium, doesn't have any half-filled orbitals. So what happens is that one of the electrons from the 2s kind of goes here, but not really. So one of the 2s one of the 2s orbitals, or the only 2s orbital, the 2s orbital combines with one of the 2p orbitals to make two new orbitals called sp hybrid orbitals. Now, sometimes we put the number 2 in front of it to indicate that this is in the second energy level, but I'm fine with just sp. And then we have two regular 2p, these ones here, unhybridized. So those two are left unhybridized. This 1p orbital combines with this s orbital to make two new hybrid orbitals called sp hybrid orbitals. We now have two half-filled orbitals, which beryllium can then use to form the two covalent bonds it needs to make this molecule. So if you don't understand that, that's fine. We'll keep going, and hopefully as we do more examples, you'll have a better understanding of what's going on here. All right, let's take a look at the next one. Another type of hybrid orbitals are known as sp2. That's not sp squared. sp2 hybrid orbitals. Here, the electrons are localized in three regions around the central atom. So the example we want to look at is boron trihydride. So it looks like that. Let's again look at the orbital diagram for the valence shell of boron. So boron has two electrons in the 2s sublevel and one electron in the 2p. So in looking at the skeletal structure here, boron needs to be able to form 3 covalent bonds. It needs 3 electron groups. In order to form 3 covalent bonds, boron needs 3 half-filled orbitals. So how many atomic orbitals will combine to give rise to 3 new half-filled orbitals? That will be 3. So how this happens is the s orbital combines this time with 2 of the 2p orbitals to make 3 new, what we call sp2 hybrid orbitals. And then this third 2p orbital is left unhybridized. I draw it up higher to indicate that the unhybridized 2p orbital is a higher energy orbital than the new sp2 hybrid orbitals. Doesn't have any implications here. And then let's distribute our electrons. 3 valence electrons for boron. Now we have 3 half-filled orbitals, which boron can use then to form 3 covalent bonds that it needs to make this molecule. Hopefully you're seeing a pattern here. Next up, we have sp3 hybrid orbitals. This time, the electrons are localized in 4 regions around the central atom. So the example we're going to look at is carbon tetrachloride. So here's our skeletal structure. In this molecule, how many covalent bonds does carbon form? It has 4 covalent bonds. In order to form 4 covalent bonds, how many hybrid orbitals must carbon make? It must make 4 hybrid orbitals. In order to make 4 new hybrid orbitals, how many atomic orbitals need to combine? Seeing a pattern here? Again, that would be 4. So this time, let's take a look at, again, the orbital diagram for the valence shell of carbon. Has 2 electrons in the 2s sublevel and 2 electrons in the 2p. Now it looks like carbon can form just 2 covalent bonds since it has those 2 half-filled orbitals. But again, something else happens where where carbon is able to combine its atomic orbitals to make new hybrid orbitals. So in this case, we have, look at the name, sp3, 1s, it's always 1s, there's only 1s orbital in the valence shell. 1s combines with all 3 p orbitals to make 4 new orbitals called sp3. Carbon then will distribute its 4 valence electrons to those 4 sp3 hybrid orbitals. Carbon now has 4 half-filled orbitals it can use to form 4 covalent bonds. So look at the number of electron groups around the central atom. That will tell you how many hybrid orbitals the central atom needs to form. And then that will help you then to determine what type of hybrid orbitals form. So going back to sp, sp hybrid orbitals look like this. So here's an sp hybrid orbital, here's an sp hybrid orbital. And how far apart are they from one another? About 180 degrees. So beryllium chloride, BeCl2, has a linear geometry. It has a linear geometry because the central atom is sp hybridized. In this example, sp2 hybrid orbitals look like this. There's 3 of them. How far apart are they from each other? About 120 degrees. So this molecule is trigonal planar. Why is BH3 trigonal planar? It's trigonal planar because the central atom is sp2 hybridized, and those hybrid orbitals are 120 degrees apart from each other. You do the same thing here, except I can't draw 4 sp3 hybrid orbitals because it really needs to be 3-dimensional. But we get 4 sp3 hybrid orbitals, all 109.5 degrees apart from each other. So this molecule is tetrahedral because the central atom is sp3 hybridized. All right, there's no such thing as sp4 since there's only a maximum of 3p orbitals in any energy level. So what if the central atom has more than 4 electron groups? We talked about this idea of an expanded octet. Those atoms, when they're the central atom that exceed the octet rule, this is how they do it. So we form something called sp3d hybrid orbitals. So in this case, electrons are localized in, you guessed it, 5 regions around the central atom. So let's look at the example of phosphorus pentafluoride. To form this molecule, phosphorus needs to form 5 hybrid orbitals. How many atomic orbitals must combine to give rise to 5 hybrid orbitals? That would be 5. Which 5 atomic orbitals combine to give rise to 5 new hybrid orbitals? 1s, 3p, and 1d orbital. Here's the thing, not all atoms can have an expanded octet. In order to have an expanded octet, the central atom needs access to d orbitals. So let's take a look at the valence shell for phosphorus. This time we have valence electrons in the 3rd energy level. And the d orbitals start in the 3rd energy level. True, phosphorus does not have any d electrons. All it needs is d orbitals. So theoretically, there's space available for d electrons in phosphorus. It just doesn't have any. So what happens in this case? The s orbital combines with all 3p orbitals in one of the d orbitals to make 5 new hybrid orbitals called sp3d. 5 valence electrons distributed to those 5 hybrid orbitals. Phosphorus now has 5 half-filled orbitals that it can use to form 5 covalent bonds as needed to make this molecule. Again, there's a pattern, sp3d2, and as you guessed it, this time the electrons are localized in 6 regions around the central atom. Oh, going back here really quickly, PF5 has a trigonal bipyramidal geometry. It has this shape because the central atom is sp3d hybridized. You have 3 hybrid orbitals around the equator, 1 up here, 1 down here to make those 5 covalent bonds. All right, for this one, we're going to use SeCl6. So in order to form this molecule, selenium needs to be able to form 6 covalent bonds. In order to form 6 covalent bonds, it needs to form 6 hybrid orbitals. In order to form 6 hybrid orbitals, 6 atomic orbitals need to combine. So like phosphorus, selenium has its valence electrons in an energy level higher than the 2nd energy level. There are no d orbitals in the 2nd or 1st energy level. In this case, we're in the 4th energy level. Selenium has 6 valence electrons. No electrons in the 4d. Has electrons in 3d, but that's not in the valence shell. 4d. And so this time, the s orbital is going to combine with all 3p orbitals and 2 of the d orbitals to give rise to 6 new hybrid orbitals called sp3d2. Selenium now has 6 half-filled orbitals that it can use to form 6 covalent bonds. And that's how the central atom is able to form, in this case, 6 covalent bonds. All right, this is not in your notes, but I want to take a look at a different example. Let's look at ammonia. We'll start off with the Lewis structure. How many electron groups are around the central atom in nitrogen? Now, granted, they're not all bonding pairs of electrons, but it doesn't really matter. So we have 4 electron groups. The electron geometry is tetrahedral. So why does this have a tetrahedral electron geometry? Well, it must be that the central atom is sp3 hybridized. So let's look at, again, for nitrogen, orbital diagram. So it looks like nitrogen can form 3 covalent bonds with hydrogen just by using its atomic orbitals. This doesn't happen though, it hybridizes. So the s orbital combines with all 3 p orbitals. Go ahead and distributes those valence electrons to those 4 hybrid orbitals. Pause the video. So what did you end up with? I think we should get something like this. 1, 2, 3, 4, 5. Notice anything? Nitrogen has 3 half-filled orbitals, which it can use to form the 3 covalent bonds to make this molecule. But what about this right here? You have one sp3 hybrid orbital that is not half-filled. It has 2 electrons in it. What's going on there? Well, that is this. So the lone pair of electrons, the electron pair that belongs just to nitrogen, also occupies a hybrid orbital. 3 half-filled orbitals. Nitrogen can form 3 covalent bonds in this case. All right, next up, bond polarity. That word polar means opposite ends. So we have non-polar covalent bonds, bonds that do not have opposite ends, and polar covalent bonds, bonds that do have opposite ends. So whether a covalent bond is polar or non-polar depends on the electronegativities of the bonded atoms. Recall that electronegativity is the tendency of an atom when bonded to another atom to attract electrons. So I gave you a little different definition there. So let's start with non-polar covalent bonds. Non-polar covalent bonds occur when the atoms bonding together have the same or very similar electronegativities. So this usually happens when the bonding atoms are identical. For example, fluorine and fluorine. You have 2 fluorine atoms bonded together. So we have, again, a tug of war. I used this analogy before. We have a tug of war with the electrons. In this case, both teams, both atoms have the same strength, they have the same electronegativity. So they're going to pull equally as hard on these shared electrons. In a real tug of war, you've got a flag in the middle of the rope. When that tug of war starts and you have 2 evenly matched teams, where does that flag go? It stays right in the middle of the 2 teams. Same thing with these 2 electrons here. Since they're being pulled equally by both fluorines, the shared electrons spend most of their time right in between those 2 nuclei. Now, it doesn't matter if it's a single bond or a double bond or a triple bond. If the 2 bonded atoms have the same electronegativities, the bond between them will be non-polar. So again, both oxygens are pulling equally as hard. They share the electrons equally. That's another property of a non-polar covalent bond, equal sharing of the electrons. Now, what if you have nonmetal atoms that are different? They have different electronegativities. Well, in this case, if the difference in electronegativity is high enough, you're going to end up with something called a polar covalent bond. So in this case, chlorine is more electronegative than hydrogen. So again, they're playing tug of war with these electrons. So let's say you have one team that's not significantly, just slightly stronger than the other team playing tug of war. What's going to happen to the flag on that rope? Well, when the tug of war starts, the flag will be pulled closer to the stronger team. Now, they're not going to be strong enough to rip the rope away from the other team. It's not like in the case of ionic bonding. Chlorine here, being the stronger atom, if you will, higher electronegativity, pulls the shared electrons a little bit away from the hydrogen, not completely off of the hydrogen. And so the shared electrons spend more time closer to chlorine's nucleus than hydrogen's nucleus. And what happens as a result is that the electrons will spend more time down here on the right side than on the left, giving the chlorine end of the bond a partial negative charge, so that is a Greek letter delta, and the hydrogen end a slightly positive charge. So you have opposite ends. This is a polar molecule. Let me show you a different way of doing this. Fluorine is more electronegative than hydrogen. So fluorine is able to pull the shared electrons a little bit away from the hydrogen. The shared electrons spend more time closer to the fluorine than the hydrogen, giving the fluorine end of the bond a partial negative charge. So the arrow is on the end of the bond that's partially negative, and the hydrogen end of the bond is partially positive. And we see it looks like a positive sign here, the tail of the arrow, indicating the region of partial positive charge. So what is the difference between ionic and covalent? Talked about this before. It has to do with the difference in electronegativity. If the difference in electronegativity is big, say 1.7 or higher, that means the bond is primarily ionic. And if the difference is less than 1.7, it's considered to be covalent. Well, what's nonpolar versus polar? Let's add that. Nonpolar is technically from 0 to 0.3 difference in electronegativity. And from 0.3 to 1.7 would be polar. Now, if you're ever unsure if it's a polar or nonpolar covalent bond, there's a table of electronegativities on page 303, and we can see if the bond is polar covalent versus nonpolar covalent. Let's take a look at an example. Between sulfur and oxygen. Sulfur has an electronegativity of 2.44, and oxygen has an electronegativity of 3.50. Pause the video. What is the difference in electronegativity? Difference in electronegativity of 1.06. So this must mean that the bond between sulfur and oxygen is polar. Let's look at another example. Look at a bond between sulfur and carbon this time. Sulfur 2.44, carbon 2.50. Difference in electronegativity 0.06. Now notice something. We have different nonmetal atoms, but because their electronegativities are really close to each other, technically this bond is nonpolar. So for this class, since we're not going to use a table of electronegativities, we'll just use the general trend in electronegativity and this generalization. If you have two of the same nonmetal atoms bonded together, of course, then that bond is nonpolar covalent. If you have two different nonmetal atoms, we'll just assume that that bond is polar. Just know that that's not always the case, but we won't do any of the exceptions in this class. So two different nonmetal atoms, the bond between them is polar covalent. All right, that's it for this lesson. Thanks for watching.